Welcome to Chapter 7, which is going to be about two of the most obvious astronomical objects in our solar system that we see on a day-to-day basis, that is to say, the Earth and the Moon. We're going to start out talking about something that is necessary for life to exist on this planet and for us to be comfortable on the Earth, which is Earth's atmosphere. Earth's atmosphere is a key part of our planet's dynamic activity and its ability to sustain life. Essential to the existence of complex life is air that contains oxygen molecules. The air we breathe is predominantly a 4-to-1 mixture of nitrogen and oxygen, two gases that are found only in small amounts in the atmosphere of other planets. The theory of planet formation and the models that attempt to reproduce the early history of the Earth indicated that the present atmosphere is the third one to envelop our planet. Earth's earlier atmospheres contained no free oxygen, composed of trace remnants of hydrogen and helium left over from the formation of the solar system. The first atmosphere did not last very long. The atoms and molecules in these gases were too light to stay near Earth. Heated by sunlight, meaning that they moved faster and faster, these particles gained enough kinetic energy to overcome Earth's gravitational pull and fly away into space. The gases of the second atmosphere came from inside Earth, vented through volcanoes and cracks in Earth's surface. That atmosphere was composed primarily of carbon dioxide and water vapor along with some nitrogen. These gases consist of more massive atoms than the hydrogen and helium in the first atmosphere. Therefore, the speeds imparted to the gases by the second and third atmospheres by sunlight were not high enough to enable most of them to leave Earth's gravitational bonds. This is why Earth developed a permanent atmosphere. There were roughly 100 times as much gas in the second atmosphere as there is today. Carbon dioxide and water store a great deal of energy in the form of heat, helping create what is called the greenhouse effect, about which we will say more shortly. The high concentration of these gases in Earth's early life stored more heat than the atmosphere does today. Earth back then would have been a serious hothouse had the sun reached its full intensity at that time. However, the sun was dimmer and cooler back then, so the high concentration of carbon dioxide and water in there actually prevented the young Earth from freezing. Oceans began forming when water precipitated out of this atmosphere, as well as the impacts of water-rich space debris, such as comet nuclei, and some asteroids mentioned in chapters 5 and 6. These events occurred within 300 million years of Earth's formation. Indeed, geologists have discovered evidence for liquid water on Earth's surface 4.3 billion years ago. As noted earlier, the oceans today cover about 70% of Earth's surface. This number can be misleading, considering that the average ocean depth is only a few kilometers, and that Earth in diameter several thousand kilometers. The total volume of water on Earth's surface is not that large. This image shows the relative size of Earth compared to a sphere containing all Earth's water and the sphere containing all the fresh water on Earth. The larger sphere is about 1385 kilometers in diameter and includes salt water from ocean and fresh waters from lakes, rivers, snow, and ice around the world, the atmosphere, and other sources. Despite coming from a variety of sources, the freshwater sphere is only about 56 kilometers in diameter. Nearly 3/4 of Earth's surface is covered with water, a substance that is essential to the existence of life. In contrast, there is no liquid water at all on the surface of any other object in the solar system. Oxygen that entered the air very early in Earth's history came from oxygen-rich molecules, like carbon dioxide, that were broken apart by the sun's ultraviolet radiation. Then came oxygen released as a byproduct of the ocean plant life activity. In both cases, this oxygen did not stay in the air for long. Oxygen is highly reactive, and early atmospheric oxygen combined quickly with many elements on Earth's surface, notably iron, to form new compounds such as iron oxides, otherwise known as rust. About 2 billion years ago, after all the surface minerals that could combine with oxygen had done so, the atmosphere began to fill with this gas. With the carbon dioxide reduced to a very low level, the air became the primarily nitrogen-oxygen mixture that we breathe today. Although nitrogen was only a tiny fraction of that earlier atmosphere, it now dominates the thinner air of today. The troposphere, the lowest part of the atmosphere, is heated primarily by Earth. which is why the temperature of this part of the atmosphere decreases with altitude. The farther away from the heat source of Earth, the cooler the air gets. However, because the ozone in the stratosphere stores significant heat from the sun above it, the temperature in the stratosphere actually rises with altitude to about its top. Note that above the stratosphere lies the mesosphere. Atmospheric temperatures again decline as you move up through the mesosphere, reaching a minimum of at about an altitude of 80 kilometers. This minimum marks the bottom of the ionosphere, also called the thermosphere, above which the sun's ultraviolet radiation heats and ionizes atoms, producing charged particles that reflect radio waves. To further explain the atmosphere, we must talk about the greenhouse effect. What happened to make your car so warm in a sunny day? First, sunlight entered it through the windows. This radiation was absorbed by the dashboard and the upholstery, increasing their temperatures. Because they become warm, the dashboard and upholstery emit infrared radiation, which you can detect as heat and which your car windows do not permit to escape. This energy is therefore trapped inside your car and absorbed by the air interior surfaces. As more sunlight comes through the windows and is trapped, the temperature continues to increase. The same trapping of sunlight warms greenhouses as well as the entire Earth. This greenhouse warming is responsible for global warming, where greenhouse gases such as water and carbon dioxide trap the heat that is emitted, or the infrared radiation that is emitted by the Earth, after you have radiation emitted by the sun, which is relatively able to get through the atmosphere transparently. And this Earth heat is, or this Earth light is going to reflect back and heat the Earth the same way that your car window is going to reflect heat back onto the dashboard and to your seats. Carbon dioxide is a major greenhouse gas, and it is also one of the main gases that is created by industry. So as we see an increase in carbon dioxide in the Earth's surface, or in the Earth's atmosphere, we see a commensurate surface temperature on the Earth that is rising alongside this carbon dioxide or greenhouse gas. Anyone who carefully examines the shape of Earth's continents might conclude that land masses move. Eastern South America, for example, looks like it would fit snugly into Western Africa. Between 1912 and 1915, the German scientist Alfred Wegener published his observations on this remarkable fit between landmasses on either side of the Atlantic Ocean, an ideal also proposed by Isaac Newton 2 centuries earlier. Wegener was inspired to advocate the hypothesis of continental drift, the ideal that the continents on either side of the Atlantic Ocean had moved apart. Then, in the mid-1950s, geologists discovered long underwater mountain ranges. The Mid-Atlantic Range, for example, stretches from Iceland to Antarctica. Careful examination revealed that mountain rock from the Earth's interior is being forced upward there as some mechanism caused the ocean floor to slide apart on either side of the ridge. This seaward spreading is moving the Americas away from Europe and Africa at a speed of roughly 3 centimeters per year. The relative motion of the plates worldwide ranges from 1.5 to 7 centimeters per year. Seafloor spreading provided the physical mechanism that allowed for Wegener's hypothesis of crustal motion to be developed into the modern theory of plate tectonics. It was after this hypothesis was confirmed in the 1960s that the theory of continental drift became widely accepted. Earth's surface is made up of 7 major and many minor rafts of rock called tectonic plates, which move relative to one another. These plates float on the slowly moving, denser matter below them. The plates have not always been separate as they are today. Sometimes they merge into a single mass called a supercontinent. In recent years, geologists have uncovered evidence that points to a whole succession of supercontinents that broke apart and reassembled. Pangaea is only the most recent supercontinent in this cycle, which repeats on average every 500 million years. The boundaries between tectonic plates are the sites of some of the most impressive geological activity on our planet. Earthquakes and volcanoes tend to occur at these boundaries, where the plates are colliding or at converging boundaries, separating at divergent boundaries, or grinding against each other at transform or transform fault boundaries. Earth has only 190 known craters caused by impacts. Tectonic plates motion helps explain why Earth's oceans have so few craters today. Countless impacts have occurred on the oceans, which cover most of our planet. Some of the impacting bodies were slowed or obliterated before cratering the ocean floor, but others were large enough or fast enough to hit the floor. The resulting craters in the oceans rolled on their tectonic plates until they reached a convergent boundary, where they were subducted, drawn underground, and thereby erased. Impact craters created on the dry land masses, continents, and islands are exposed to the atmosphere. Wind and water erode them, with silt from rivers helping to cover any remnants. Only the youngest craters on Earth remain visible. What powers all this activity? Some enormous energy source must be shifting land masses, and it must have been doing so for billions of years. The answer to that question leads us to a scientific model of Earth's interior. Analysis of seismic recordings led to the discovery that Earth's solid core has a radius of about 1,250 kilometers, surrounded by a molten iron core with a thickness of about 2,250 kilometers. For comparison, the overall radius of our planet is 6,378 kilometers. The cores are composed of roughly iron and lighter elements such as nickel, oxygen, and sulfur. The interior of our planet, therefore, has a curious structure. A liquid region sandwiched between a solid inner core and a solid mantle. You might think that a temperature such as that seen in the center of the Earth would melt any substance. The mantle, in particular, is composed largely of minerals rich in iron and magnesium, both of which have melting points which are below the temperature of the mantle itself on Earth's surface. However, the melting point of any particular also depends on the pressure at which it is subjected. The higher the pressure, the higher a material's melting point. The high pressures within Earth, 1.4 million atm at the bottom of the mantle, keep the mantle solid to a depth of about 2,900 kilometers and also allow for a solid iron core in the center of the planet. Although it is solid, the mantle can slowly fall and deform, analogous to the behavior of silly putty. The mantle rests on an iron core below which the pressure is so high that it compresses into the very hot iron and other dense atoms there to form a solid inner core. And then using convection, or the motion of heat and energy through the motion of fluids, this is able to cause there to be the continental drift that we talked about earlier, in the same way that convection in a heated up pan causes there to be motion of the water molecules on the surface of boiling water. The motion inside of Earth's surface, or on the inner side of Earth, also causes there to be a magnetic field, which is a physical phenomenon which is caused by the motion of charged particles, such as the charged iron in molten magma. This magnetic field helps to protect us from the solar wind, or charged particles that come out of the sun, which are deflected by the magnetic field so that they don't come at our planet by itself, but instead pass harmlessly by. Earth's magnetic field also traps some of the solar wind particles in two huge donut-shaped rings called the Van Allen radiation belts, here after Van Allen belts, which surround the Earth. The region between these two belts fills up with the charged particles, which are drained by lightning on Earth, making the region unstable. These belts, discovered in 1958 during the flight of the first successful U.S. Earth-orbiting satellite, were named after the physicist James Van Allen, who insisted that the satellite carry a Geiger counter to detect charged particles. When the flow of particles from the sun is particularly high, some of the solar winds that is trapped in the Van Allen belts is funneled towards Earth's polar regions, where these particles descend and cascade down into Earth's atmosphere, usually in a ring-shaped pattern. As these high-speed charged particles collide with gases in the atmosphere, the gases fluoresce, giving off light, like the gases in a neon sign. The result is a beautiful shimmering display called the Northern Lights Aurora Borealis, or the Southern Lights Aurora Australis. depending on the hemisphere in which the phenomenon is observed. Occasionally, violent events on the sun's surface called solar flares and coronal mass ejections send bursts of high-speed, high-energy protons and electrons straight through the Van Allen belt and into the atmosphere. These solar events partially deplete the ozone layer and cause spectacular auroral displays that can often be seen over a wide range of latitudes and longitudes. These solar events also disturb radio transmissions and can damage communication satellites and electric transmission lines. In this era of burgeoning satellite usage and human space travel, the effect of the sun's electromagnetic radiation, along with the flow of particles from it and other sources of Earth's atmosphere, and on astronauts are increasingly important. As a result, space weather satellites are now continually monitoring our neighborhood in space and warning about solar events that could imperil both humans and machines out there. We now turn our attention towards the moon and some of the meteorites that create craters on the surface of the moon. Craters larger than about 20 kilometers in diameter often form central peaks. These features occur because the impact compresses the crater floor so much that afterward the crater rebounds and pushes the center upwards. As the central peak goes up, the crater walls collapse and form terraces. Is it possible to identify the relative age of craters using radio signals sent from Earth that strike the moon, scatter off it, and return to Earth, where they are assembled into photographs? The heat generated by the impacts that form craters causes the surface rock in young craters and the ejecta from these craters, which are ejected rocks that form on the opposite side of the impact, to be smoother and less powdery than the surrounding surface, called the geolith, from the Greek meaning blanket of stone, which has been converted to powder by billions of years of impacts from the solar winds and cosmic rays. The smoother, younger craters reflect more of the radio signals from Earth than does the surrounding powder. Therefore, young craters and some of the surrounding ejecta from the crater-forming events are brighter than the radio wave-absorbing regolith. As craters age, their rocks become more powdery and therefore darker in the radio images made of them. Besides its craters, the most obvious characteristics of the moon visible from Earth is that its surface is various shades of gray. Most prominent are the large dark gray plains called maria. The singular form of this term, mare, means sea in Latin and was introduced in the 17th century when observers using telescopes thought that these features were large bodies of water. We now know that no liquid water exists on our satellite. Nevertheless, we retain these poetic, fanciful names, including Mare Tranquillitatis, Sea of Tranquility, Mare Nubium, Sea of Clouds, Mare Nectaris, Sea of Nectar, and Mare Serenitatis, Sea of Serenity. As introduced in Chapter 6, and as we will discuss further shortly, Maria are basins on the moons that were filled with lava, perhaps during the late heavy bombardment. One of the largest of the Maria was Maria Imbrium, Sea of Showers. This mare is roughly circular and measures 1,100 kilometers in diameter. As seen here. The dark, extensive Maria on the near side of the moon, called Oceanus Procellarum, or Sea of Storms, has until recently been thought to be either the result of large asteroids striking the cratering the moon during the late heavy bombardment or due to the impact of a smaller second moon that spiraled out into the present moon. In either case, lava was thought to come out of the moon's interior through these impact sites because the crust was particularly thin there. These theories are consistent with the apparent circular structure of the Maria. However, the two Grail satellites orbiting the moon between 2011 and 2012 discovered that the surrounding of the Mare is a sea of rift valleys similar to the rift valleys on Earth. This led to another theory, that the lava formed without the Mare flowed out of the rift valleys, like lava flows out of similar features on Earth, without the need for a major impact to create the Oceanus Procellarum region in the first place. As you can see, these rift valleys form a rectangular boundary around the Maria, inconsistent with their being created primarily by impacts, which would create circular boundaries. Lunar geologists proposed that these rift valleys formed after the moon's crust had solidified as if it was responding to the magma under its surface. Understanding this region and the rest of the moon, for that matter, is really a work in progress. There has apparently been lava flow onto the surface of the moon as recently as 50 million years ago. Features called lunar domes are the remnants of this activity. They have been seen on both the near side and the far side Maria. They are formed when lava oozes out of the moon's surface at those locations, thereby creating shield volcanoes. If there is a lower land surrounding a volcano, the lava flows out and downhill until it levels around the surrounding area. Then the lava starts to collapse upon the central dome or peak where the lava flow ceases. The central region of the dome where the lava came out often collapses to create a crater. This is due to the remaining liquid lava inside solidifying and contracting as it occurs to create rheas. Volcanoes, the accepted lunar domes, are lower than a few hundred meters high and less than 20 kilometers wide. At least 70 lunar domes have been identified. Analogous phenomena occurred on Earth, Mars, and Venus. In comparison, shield volcanoes build up as high as 9.2 kilometers on Earth, Mauna Kea in Hawaii, 25 kilometers on Mars, Olympus Mons, and 8 kilometers on Venus, Mont Mons. Shield volcanoes differ from stratovolcanoes like Mount Etna, Mount Vesuvius, and Mount Fuji, which violently eject lava. The flat, low-lying, dark gray Maria cover only a portion of the lunar surface. The remaining is composed of light gray, heavily cratered mountainous regions called highlands. One mountain range created by an impact can be seen around the edge of Mare Imbrium. Although they take their names from the famous terrestrial ranges such as the Alps, the Apennines, and the Carpathians, the lunar mountains were not formed through plate tectonics, as were mountains on Earth. Their formation... Astronauts discovered that the lunar surface is covered with fine powder, the regolith mentioned earlier, and rock fragments. The regolith ranges in thickness from 1 to 20 meters. The regolith formed during 4.5 billion years of relentless micrometeorite bombardment and pulverized the surface rock. We do not refer to this layer as soil because the term soil suggests the presence of decayed organic matter which is not found on the moon's surface. This indicates that the Maria developed about 1 billion years after the moon formed and that the Maria were formed from molten rock, consistent with this material poured out of the moon after the late heavy bombardment. These Maria rocks are composed mostly of the same mineral that are found in volcanic rocks in Hawaii and Iceland. The rock of these low-lying lunar plains is called Mare basalt. In contrast to the dark Mare basalt, the lunar highlands are covered with anorthosite, a rock that is somewhat lighter than basalt. On Earth, anorthosite rock is found only in very old mountain ranges such as the Adirondacks in the eastern United States. Many highland rocks brought back to Earth are impact breccias, which are composites of different rocks fused together as a result of meteorite impact. With several seismic detectors working simultaneously, geologists were able to deduce information about the moon's interior from the timing and strength of the vibrations that were detected. The data suggests that the moon has a small iron core, possibly a layer of hot rock above it, and a thick layer of solid rock above that, surrounded by the crust. The presence of the iron core, accounting for only a portion of the moon's mass, was confirmed by data of the Lunar Prospector satellite in 1998. This is a small proportion compared to Earth's core, which, like Earth, the moon's interior was molten early in its life. Because the moon is smaller than the Earth, it initially had less heat stored inside. Heat from cooling inside both worlds leaks out through their surfaces, with the smaller moon cooling faster. Since 2009, NASA's Lunar Reconnaissance Orbiter has provided us with exquisite 3D images of the lunar surface, with resolution as fine as 0.5 meters. Besides the lunar domes, two other sets of features on the moon's Maria, graben and wrinkle ridges, also show how its surface has changed in relatively recent times. Most graben are found near the edges of Maria. They formed when nearby regions of a surface separates, allowing the intervening land to descend. Graben look like long troughs and may have formed as recently as 50 million years ago. Depending on how recently they formed, the graben could indicate that the inside of the moon may still have some magma that has caused the surface to move. In recent years, graben have been found on other regions of the moon, including the highlands on the far side. Wrinkle ridges were discovered in the 19th century. They generally rise above the surrounding surface of the Maria and run in a few variety of patterns. Wrinkle ridges are typically between a few meters and a few hundred meters high, between a few tens of meters and 20 kilometers wide, and between a few hundred meters and 200 kilometers long. While some wrinkle ridges are smoothly curved, many are asymmetric, with one side being steeper than the other. Their origin is still being explored. One theory has it that when the lava filled the basins destined to become Maria, the weight of this lava caused parts of the underlying rock to sag. As a result, the upper layers moved down unevenly, with some regions creating the wrinkle ridges and others creating graben. Another theory proposes that while the crust below new lava remains rigid, the lava flows over wrinkle ridges that existed in the underlying rock were forced upward to create wrinkle ridges of the surface today. Since spacecraft began orbiting the moon, scientists have known that their orbits do not follow the elliptical paths predicted by Kepler's law. Every once in a while, usually over a mare, the spacecraft momentarily dips moonwards as they are pulled by a higher than normal concentration of mass. These mass concentrations, or mascons, are local regions of relatively dense rock and metal near the moon's surface. The mascons found in the Maria are believed to be the magma that filled the bottom of the mare. The magma solidified after emerging from inside the moon. Before the mascons were well understood, a small satellite put in orbit in 1972 came under their influence, and their stronger than average gravitational tug caused the satellite to crash into the moon. The satellite, intended to orbit for years, lasted only 35 days. The presence of water on the moon would greatly simplify human settlement there, not only for its unusual roles in our lives, but also because the separated atoms of oxygen and hydrogen from the water can make rocket fuel and breathable oxygen, as well as generate heat and serve as fuel to generate electricity. The space shuttle's primary rocket engine, for example, was fueled by liquid oxygen and liquid hydrogen. Separating the moon's water into liquid oxygen and liquid hydrogen would create the same fuel. An existing water reservoir makes establishing a lunar colony much less expensive and more feasible than lugging all of that water from Earth or dragging a water-rich comet to the moon. Before the Apollo program, scientists debated three different theories about the origin of the moon. The fission theory held that the moon was flung out from an extremely rapidly rotating proto-Earth, but no geological evidence supports Earth ever spinning fast enough for this to have occurred. The capture theory posited that the moon was formed elsewhere in the solar system and then drawn into orbit around Earth and gravitational forces. However, the capture of such a large moon would require it to originally have had a moon of its own, which was flung away from it as those two bodies passed near Earth. That is possible, but very unlikely. Furthermore, because bodies formed in different places have different overall chemical compositions, this theory does not explain the extremely close geochemistries of the surfaces of the moon and Earth. The co-creation theory proposed that the Earth and the moon were formed near each other at the same time. As with the fission theory, this theory fails to explain why, compared to Earth, the moon has less of the denser elements such as iron that exist in vast amounts deep within Earth. Several other theories are now being explored. The most well-developed, called the collision ejection theory or giant impact theory, was first proposed in 1975. It applies the established fact of age-old collisions in the solar system to the formation of the moon. Despite its explaining two phenomena resulting from one event, the collision ejection theory is now facing some challenges. The study of space debris found on Earth in the form of meteorites reveals that objects formed in different parts of the solar system have different chemistries. If Theia was not formed in Earth's immediate vicinity, then it was likely that the two bodies had such chemical differences. One example is like the isotopes of oxygen. Oxygen can either have 8, 9, or 10 neutrons in its nucleus. These isotopes are found in the different amounts on Earth and on other bodies in the solar system. However, the moon rocks brought back by Apollo astronauts and meteorites splashed off the moon, and that subsequently struck the Earth, first discovered in Antarctica in 1979, have the same ratio of oxygen isotopes as does the Earth. This ratio is different for all the other worlds in our solar system. The same applies to other chemicals on Earth and the moon. So if Theia was not formed in the Earth's immediate neighborhood, it is unlikely to have been the origin of most of the moon's mass. As said before, Earth and moon orbit a common center called the barycenter, and this motion is crucial in understanding the cause of the moon's tides, but before explaining them, it is instructive to introduce another tide-related issue, namely that the rate at which the moon orbits the barycenter and the rate at which it rotates is the same. If the moon's orbit were perfectly circular, if the moon's rotation axis were perpendicular to the plane of its orbit around Earth, if the moon were orbiting in the plane of the ecliptic, we were unable to observe the moon from different places on Earth's surface, and if we always saw the moon in the same distance from Earth throughout the month, then we would see precisely 50% of the moon's surface. In fact, none of these statements is true. As a result, we see a little beyond the poles and around the sides of the moon. We can see about, I think it was 58% of the moon's total surface from Earth at different times throughout the year. The changes in what we see of the moon from Earth is called the motion of the moon, as due to our motion and the moon's motion around the barycenter are called librations. It is also worth noting the effect that the moon has on the Earth and that the Earth has on the moon. So the gravitational pull of the Earth and the pull of forcing out causes there to be a net force that is called F tide, or the force of tides. So as the moon is moving around the Earth, it pulls harder on different parts of the Earth, which causes the Earth to slightly bulge at that point. This is also true of the sun, and the sun actually has a greater impact on a greater impact on the pulling the Earth's tides or the Earth's oceans than the moon does. However, the moon has more variance because from one side of the Earth to the other is a great change in the moon's gravitational pull, while from the sun is so far away that there is a small change in the Earth's gravitational pull. This causes there to be tides, which are the motion and the ebb and flow of water in the Earth, as well as the ebb and flow of materials on the moon. And then another thing to note is that using this, we can finally explain the moon's synchronous rotation. When the moon was young, it was molten, and Earth's gravity created huge tides of molten rock up to 18 meters high there. Friction generated by these tides between the liquid rock and the mantle below it caused the moon to speed up or slow down. We do not know which until one of the high tides became fixed directly between the moon's center and the center of the Earth. As the surface solidified, it locked into the interior, causing the entire moon to rotate at the same rate as its surface. The entire moon was then in synchronous rotation. Despite it always having the same side face Earth, the moon still has small tidal deformations. This comes from the fact that its orbit around the Earth's barycenter is not circular. Sometimes it is closer to the Earth than other times. As a result of this change in difference, the moon feels a change in gravitational force, which causes it to change its shape. Sometimes it is more spherical than other times throughout each orbit around the barycenter. These changes in shape, tidal distortions, are between 10 to 20 centimeters each orbit.